For the introduction part, the bombings of Hiroshima and Nagasaki were two significant events that occurred during World War II, specifically at the end of the war in 1945. These bombings involved the use of atomic bombs by the United States against Japan, resulting in massive destruction and loss of life. The B-39 bomber named Boxcar released the fragment bomb over the city of Nagasaki. The explosions occur about 500 meters above the ground and unleash an enormous amount of energy. The atomic bombs made by the Allied powers, which is from USA and UK, from Plutonium-239, were dropped on Nagasaki early in August 1945. Plutonium has several isotopes that are really dangerous and very hazardous. Pu isotopes are regarded as highly hazardous pollutants in the environment due to their radiological toxicities and very long radioactive half-life, which lead to long-term persistence in the environment. So there are two samples and chemicals that are potentially found in the incidents. The first one is solid sample. Solid and sediment are one of the samples that have been collected like radioactive isotopes. It contains radioactive isotopes such as Ca-137, Strontium-90, and residual amount of uranium and plutonium from the atomic bomb's detonations. The second one is water sample. It is from rivers, streams, and well would likely contain trace of radioactive isotopes from the blast, such as Ca-137 and Strontium-90. There are several methods that can be used to collect the sample from Nagasaki bombing. For solid samples, preserve and store the samples with handle collected samples with care and store them in appropriate containers or preservation methods that prevent further degradation or contamination. The second one is safety precaution. This may involve wearing protective equipment (PPE), utilizing specialized tools, or conducting sample analysis in controlled environment. To collect water sample from affected area of Nagasaki after the bombing, the following sampling method could have been employed, which is two. The first one is grab sampling and composite sampling.
One of the initial steps in the analysis plutonium is sample action treatment. The process involves breaking down organic material present in the ambient matrix. So etching is necessary to ensure accurate and precise measurement. Currently, the most popular technique for sample ligation is nitric acid ligation. However, there is some limitation such as long processing time. To address this challenge, microwave assisted ligation has been implemented. This technique offers shorter processing times, improved recovery rate, and the less use of less strong acid. Another widely used method is the fusion method. This technique involves subjecting the sample to the high pressure to achieve complete decomposition. Compared to the acid ligation, fusion method offers higher recovery of plutonium and increase treatment efficiency. So, when it comes to concentrating plutonium in liquid sample, which large volume. Okay. Next, we go to the how to purify and separate plutonium isotopes. Several techniques are commonly used, including extraction chromatography, liquid extraction, IUS-gen, or combination of this method. One important aspect of purification process is to convert plutonium ion in the solution to plutonium-4 oxidation state, since Pu4 is primarily used for purification. So the reduction reaction of plutonium ions can be accelerated by heating or by using reducing agents such as ferrous ion ascorbic acid. It is recommended to carry out the separation in the hydrochloric acid system, as PU3 is easily oxidized in nitric acid. So, liquid extraction is commonly used method for separating plutonium in radioactive waste treatment. However, the process can be time consuming and poses a threat to environment due to the multiple extraction required for complete removal of the plutonium from.
Next, I will continue with comparison of detection method. The most suitable method is alpha spectrometry. Based on the research, there are some factors that to be considered. The first one is detection limit. Some methods have high detection limit for 241 Pu isotope, which means it is less sensitive. But for alpha spectrometry, have a quite low detection limit for that isotope. For detection time, alpha spectrometry require longer time than other method, but it's okay depending on the urgency of the analysis. Next, the accessibility for alpha spectrometry is also good, while other methods require expert and good technology. As example, AMS require high-skilled staff because it is more complicated, while RIMS is quite restricted due to its facilities and equipments. Lastly, the cost for alpha spectrometry is quite affordable compared to other methods. So, the best and the most suitable method is alpha spectrometry.
For analysis method, there are two major methods that has been used by the article that we studied, which are the radiometric method and the mass spectrometry method. Both methods have their own advantages and disadvantages. More suitable method should be used depending on the situation. The first one is the radiometric method that is divided by the two methods, which are the alpha spectrometry and the liquid scintillation counting (LSC). For alpha spectrometry, plutonium isotope identification still relies heavily on alpha spectrometry, which is a classic radiometric counting technique. Because of the ease of measurement, good spectral resolution, and reasonable sensitivity for certain radionuclides, particularly those with short half-life, semiconductor alpha spectrometry has been widely accepted as a strong technique, despite the inexpensive equipment costs, and this detection technique demands extremely long counting periods of time, which from 1 to 30 days. As a result, spectrometric detection is inappropriate for emergency scenarios in which analytical result must be provided in a shorter period less than 1 day. Other than that, due to the poor energy resolution of alpha detectors, alpha spectrometry failed to distinguish between plutonium-239 and plutonium-240. Alright, next for the liquid scintillation counting (LSC). LSC is one of the best way to analyze plutonium in the environmental sample. Because its low energy resolution, LSC cannot compete with alpha spectrometry. Furthermore, one of the disadvantages of LSC is LSC result depends on the chemical recovery given by alpha spectrometry and the complicated efficiency calibration of the instrument. For the mass spectrometry allows for the independent determination of plutonium-239 and plutonium-240. Plutonium-238 and the combined intensity of plutonium-239 and plutonium-240 are often determined with traditional alpha spectrometry. Mass spectrometry is an atom counting technique that solves some of the limitations of standard radiometric, which are the alpha spectrometry just now. Example of mass spectrometry such as inductively coupled plasma mass spectrometry (ICP-MS), thermal ionization mass spectrometry (TIMS), accelerator mass spectrometry (AMS), and resonance ionization mass spectrometry (RIMS). These are the three instruments of mass spectrometry, which are ICP-MS, AMS, and TIMS. ICP-MS is more common for determining trace and ultra-trace levels of plutonium in environmental samples. Because of its high sensitivity, short analytical times, relatively simple operation, multi-isotopic detection. There are two ICP-MS that have been successfully applied to determination of plutonium in various matrices, such as sector field ICP-MS, SF-ICP-MS, and laser ablation ICP-MS, LA ICP-MS. One of the disadvantages of ICP-MS is that because of the extremely low plutonium concentration in the environment, as well as high salt and organic matter content, frequently can cause the signal suppression, and as the result, if the accuracy to the technique is poor. AMS is the most sensitive detection techniques for several long-life radionuclides. For plutonium-239 example, detection limits are as low as 10 to the power of 6 atoms. Furthermore, when compared to ICP-MS, AMS has substantially reduced metric interference effects, and the main benefit of AMS over traditional mass spectrometry, DMS or ICP-MS, is because of the total elimination of molecular isobars. Fifield in 1996 reported that the first quantitative use of AMS to the measurement of plutonium isotopes in environmental samples at level lower than those achievable with existing techniques such as alpha spectrometry and ICP-MS. Alright, the next method is the thermal ionization mass spectrometry (TIMS) and resonant ionization mass spectrometry (RIMS). TIMS is considerably more sensitive and precise than ICP-MS when measuring isotope ratios. This is because isotope ratio measurement give high precision, which they narrow down to 0.002%, which prove that this method is precise. Effort in 2005 used TIMS to analyze soils and sediments in order to calculate the plutonium-240 and plutonium-239 ratios. Apart from the high precision of the TIMS, the disadvantages of TIMS is it needs a costly equipment and strong separation to guarantee the analyte's continual ionization. Due to the laborious pre-concentration of plutonium on a filament, this method is also exceedingly labor-intensive, and also it is time-consuming and cannot be utilized for continuous detection. Right, on the other hand, for trace analysis of long-lived plutonium isotopes, RIMS performs well. RIMS has a high sensitivity due to the huge atomic cross-section of the excitation, ionization process, and the high detection efficiency. A detection limit of 10 to the power of 6 to 10 to the power of 7 plutonium atoms has been achieved for the overall isotopes, regardless of their half-life and decay modes. Lastly, when compared to the recruitment of tin sources for alpha spectrometry, the high sensitivity of RIMS encourages the use of a simplified approach for the chemical preparation of.
In conclusion, we present in this article a review and critical comparison of recent analytical methods for determining plutonium isotope in environmental matrix. Solid sample undergo several process steps to extract plutonium isotope. These steps including drying, etching, acid or alkali digestion, and cold precipitation. On the other hand, liquid sample required filtration, evaporation, and cold precipitation for further analysis. The ion exchange method is one of the common used technique, which offers simplicity and unattended operation. However, it was limitation in terms of selectivity. It is faster and easier to use than other methods, but struggle to efficiently separate complexes mixture. In contrast to ion exchange method, the extraction chromatography method is more flexible, highly selective, and moderate sensitive. Although it requires more time and effort to set up, its selectivity and sensitivity make it ideal for the separation complex mixture. When compare the two methods, we found that the ion exchange method is faster and easier to use, but lack of the separation efficiency of the extraction chromatography method. On the other hand, the extraction chromatography method provide superior selectivity and sensitivity, make it suitable for the complex mixture. Moving on to the detection method, two widely used techniques are ICP-MS and alpha spectrometer. Alpha spectrometer is cost-effective and easy to perform, but accurate quantification requires high analyte concentration and long measurement time. In contrast, ICP-MS offer high sensitivity and short analysis time. It is relatively simple to use and capable to detecting multiple isotopes simultaneously. Moreover, it allows quantification using an aqueous standard solution.